So thank you for inviting me, and it's a pleasure to be back here. About 2 years ago, I became interested in condensed matter physics, and I've written a bunch of papers. So I'll cover material which can be found in these papers. I will almost not mention these papers later in the references, and except a few occasions. And there were two reasons for my interest in condensed matter physics. First of all, it became clear that condensed matter physicists have uncovered a huge set of interesting quantum field theory phenomena that had not been fully appreciated earlier by other practitioners of quantum field theory or people coming from the high energy community. And since there are all these exciting phenomena, I was interested in understanding them. The second motivation I had was already alluded to in Wang's beautiful talk yesterday. I was here 2 years ago, in fact it was almost exactly to the day 2 years ago, and I gave a talk with the title, What is Quantum Field Theory? And a number of people here in the audience today were then in the talk, which can be found online. And in the talk, I expressed my frustration in not understanding quantum field theory in a fully satisfactory way. So reading all these condensed matter papers, I found that condensed matter physicists, by and large, think about quantum field theory quite differently than high energy physicists. And I think that the 2 points of view are complementary. It's not that one is better than the other. Every one of them has its advantages and disadvantages, and I think we can learn from each other. And since it has been quite an uphill battle for me to go through these condensed matter papers, I thought in the first few slides of this talk, I will summarize my understanding about the similarities and the dissimilarities between the different views on what quantum field theory is. So I'm happy to be corrected, but let me start. I'll explain that. I'll have a slide explaining. Okay, so I'll make that very precise later. And in some cases, surprisingly, it's the same thing. We use it different things, but they coincide on some overlap. I believe that the way we use it is broader, and it includes, I don't know all the ways mathematicians use it, but I think they use many of the things that mathematicians use, and I'll give examples of that later in the talk. So I'll define what I mean by the first word. I think the other symbols, the second one is conventional. This symbol is a little bit more mathematical. And talking about 2 plus 1, I'll try to be careful because of the mixed audience to avoid confusion and always say plus 1. In the slides, I proofread it. I think I got all of them straight. When I talk, I'm sometimes careless. And if I don't have plus 1, then now I'm always using the high energy physics terminology. So subtract 1 and add plus 1, and then it would be consistent. That's correct. Yeah, I'm always happy to hear deep, insightful comments from the audience. So how do condensed matter people think about quantum field theory? That would be highly, highly oversimplified, but I would like to stress the similarities and the distinctions. So we start from some lattice Hamiltonian or lattice Lagrangian. Doesn't matter. The Lorentz invariance will play no role in this talk. So I'm going to assume Lorentz invariance, but I don't think it's essential. And they write some complicated lattice Hamiltonian with some spins or what have you, with lots and lots of terms that can be written nearest neighbors, next to nearest neighbors. We can also add more degrees of freedom, subtract degrees of freedom, add slaves and their rulers and so forth. There's a huge space of couplings. So this is an enormous space. Enormous space. From my perspective, it's way too big. It's unmanageably big. And then they are interested in exploring all possible phases that can be found at long distances. by moving in this huge space of couplings. So we're on the lattice. That's the first thing I emphasize here. We have a lattice, and we allow all possible things on the lattice. This is a huge space. And we ask, what can we find? So this is the question, this is the answer. And the question is very, very broad. High-energy physicists, on the other hand, have the same goal here, but the starting point is much more limited. We are only interested in continuum field theories. About 2 or 3 weeks ago, a famous senior condensed matter physicist, we had one of our famous standard debates between the two perspectives, and his response was, the problem with you, Nati, is that you are too tied to the continuum. So I'll be tied to the continuum in these talks. There's an analogous thing in math. Some people love the lattice. Some people like to discretize everything. Others like to think about the continuum. And the 2 points of view complement each other. It's not that one of them is better than the other. I'll just take another one. Now, this space of couplings is considerably smaller than the previous one, because I have a finite number of fields. I'm only going to turn on the relevant operators, the relevant coupling constant, maybe infinitesimal values for the irrelevant couplings. So this space is finite dimensional, to be distinguished from the space in the condensed matter problem, which is infinite dimensional in a very big infinity. So the problem here is much more concrete, much more limited.
Why is it fixed finite?
It's fixed per problem. In another problem, there would be another fixed answer. So for example, if I'm in 4 dimensions, in 2 plus 1 dimensions, and I have a scalar field, then I can write a kinetic term, I can write a phi square, I can write a phi cube, I can write a phi fourth, and that's it. So there's a small number of coefficients. That's 2 plus 1. In 3 plus 1, the coefficient of phi to the fourth has to be infinitesimal because it's really irrelevant. In 3 dimensions, in 2 plus 1 dimensions, what I said is correct. It's a finite set. And we can argue whether it's 2 couplings or 3 couplings or 4 couplings, but it's a finite set. To be distinguished from putting some degree of freedom on the lattice and writing whatever you want.
How can you tell if it's infinitesimal in one dimension, not the other?
It's the dimension of the operator. So we start in the UV from some fixed point. In most cases, it's free. We'll write all the operators, and we are only interested in the relevant operators, not in the irrelevant operators. This is very similar to what happens in mathematics when you study singularity theory. There's a small number of deformations that are really interesting. The rest don't matter. It's completely analogous to that. So much smaller set of couplings, more limited starting point. But that means that if we get results, the results will be a lot more concrete, because we'll have results in a much smaller set of couplings. It's not that somewhere in the space of couplings we can find some phase. Instead, we'll have that phase in a very well-defined set of coupling constants, much smaller. The second place, and this is a slide I actually added yesterday in view of discussion here, is that anomalies are viewed differently. So the condensed matter people, by and large, view anomalies differently, and here I emphasize I'm only talking about 't Hooft anomalies. Recall my talk from last week, where I distinguished 3 kinds of anomalies. The first makes the theory inconsistent. The second says that the theory is consistent, but the symmetry is not there. And the third says that there's nothing wrong with the symmetry, but there is some anomaly that's such that we cannot couple it to background fields. And to make it clear, because there was some discussion about that yesterday, in condensed matter physics, we limit ourselves to the lattice, and the symmetry should act on site. They also discuss symmetries that do not act on site, but for the sake of this discussion, all the symmetries act on site. And if they act on site, it really means that there are no 't Hooft anomalies. So we say the lattice has some spins, and the spin is, say, on a circle, and we say at every point we can rotate the spin separately. There are other symmetries that do not act on site. For example, you slide the whole lattice by 1 unit. That does not act on site. Symmetries that act on site do not have 't Hooft anomalies, and if there are 't Hooft anomalies in the system, because, for example, they do not act on site, you need to add a bulk. That is to be distinguished from what we say. In high-energy physics, first of all, we don't have the lattice, so there's no question of on-site or not on-site. And second, toothed anomalies are possible. In fact, they are quite typical. Most Lagrangians that you write down that have symmetries have a toothed anomalies. That's this. There's the third. The first two I'm not even discussing. The first says that the theory is inconsistent. No reason to discuss it. The second is that the symmetry is not really there. So say, okay, it's not there, so we just throw it out of the list of symmetries. We don't discuss it anymore. The third is the more subtle and more interesting. This is the one, the theory is consistent. The symmetry is there, no problem there, but we cannot couple it to background fields. And I'll give some examples later.
Does on-site correspond to internal symmetries in field theory that don't move points of space or space?
So no, we have internal symmetry. In the lattice, yes. In the continuum, there are internal symmetries that don't move anything, and they typically have anomalies. And here are two examples. If you just write ordinary QCD, it has chiral symmetry, and the chiral symmetry has toothed anomalies, and these toothed anomalies that exist in the real world really have physical consequences. So it's not that, yeah, we high-energy physicists like to discuss these abstract things. This exists in the real world, and it has physical consequences. The Wezumino term is what captures these anomalies, and there are processes that really follow from these anomalies. These are internal symmetries. Well, here the symmetry is really approximating QCD, but the standard model itself of QCD, as it stands with massless neutrinos, we can later make it more complicated, but strictly speaking, the standard model of particle physics has a global U1 symmetry, B minus L, and that symmetry has a toothed anomalies. So again, saying, oh, we are interested in field theory, but we do not want to discuss systems that have symmetries with the toothed anomalies is clearly too limiting. It's clearly too limiting. It doesn't describe the real world. So that's an important point that should be emphasized. But here we get something interesting. We cannot couple this system to background fields. And if we do want to couple them to background fields, we have to add the bulk. So this is really the distinction, the two different views of anomalies. And in these talks, A, I'll be in the continuum, and B, I will take the high energy view that there are global symmetries. They typically have a toothed anomalies, and these toothed anomalies have consequences. Now, Dennis asked me, what do I mean by duality? So that's my one-slide summary of what I mean by duality. And I'm not going to give a definition. Instead, I'm going to give examples that they fall in classes, and then in each class, the definition will be clear. Class number one, this is a lattice or continuum model that can be described exactly in two different ways. So an example on the lattice is that we have the Ising model in 1+1 dimensions. We write it on the Euclidean lattice. There is Kramer-Vanier duality of the Ising model. This is an exact rewriting of the lattice model, and it has all sorts of interesting consequences. Another example is just Maxwell theory, quantum mechanical electrodynamics, U1 gauge field, and it has electric magnetic duality that is easily exchange E and B, and that's the same as in mathematics. The third is much more interesting. Third example is n equals 4 super Young-Mills in 3+1 dimensions. That's an exact rewriting of the same system using electric or magnetic variables. Here we do not know how, in the first two examples, we know how to do it explicitly. In this case, we don't know how to do it explicitly, but there is no doubt that the statement is true. N equals 4 super Young-Mills has such a self-duality which exchanges the coupling with another coupling. Much more common are a class of models that are known as infrared dualities. These are two different models, not to be confused. They are really different, but they have the same behavior at long distances. And examples are particle vortex duality that I explained in detail last week. These two are different Lagrangians in the continuum, but they flow to the same non-trivial fixed point. Another example is a whole set of examples in 3+1 dimensional n equals 1 supersymmetry, which will actually be quite similar to phenomena I'll discuss here. And they are further divided into two classes. In class number one, we have two distinct theories in the UV at short distances. This is my attempt to write something in ultraviolet. And that's my attempt to write something in infrared. We have the same non-trivial fixed point at long distances. So that's an example number one. And that's not, this sounds a lot like universality, but it's not. In universality, we change the parameters here to find the other point, talking about the basin of attraction of a certain fixed point. Instead here, the degrees of freedom in theory A and the degrees of freedom in theory B are related to each other through a non-local transformation. In most cases, we don't even know what it is. And in most cases, there isn't really a formula. Variable 1 is a non-local expression because the statement is only true under an integral. And I'll give examples to that later that are familiar. Example 2 is in a way more interesting, where at short distances we have theory A, and at long distances we have theory B. So these two theories really have the same long distance behavior, because this one flows to that, and this one doesn't flow. And this is a little bit more interesting, because theory A is interacting and complicated, and theory B is either free or already conformal. In that case, this is the question, and this is the answer. And we had examples of these two phenomena last week when we discussed cases of duality. That's right. So that's an example of that. So this is the SU2, and this is the abelian theory that is dual to it. This is last week I had examples of interacting theories here and a free fermion here. There are also examples like that both are UV free and they become strongly coupled. And in which case, okay, they both flow to the same thing, and sometimes we learn more by exploring A, sometimes we learn more from exploring B, but it's not an exact solution of the long distance behavior, whereas here it is an exact solution of the long distance behavior. Yes?
Yeah, we'll say same non-trivial fixed point at a long distance. So that sounds like a near a critical point.
Okay, I was a little bit imprecise here. They could also have the same first order transition. So for the purpose of this talk, we'll not be able to distinguish, except when I say explicitly that there is really a second order transition. So what I really mean is that I explore the parameters of theory A, look for a second order point, explore the parameters of theory B, look for a second order point, and then if I found in one, the claim is that there must be one in the other. If I find in either, and the transition is first order, we should be able to find the same first order transition. So the statement is that the infrared behavior is the same. It distinguishes between the two phases, and if there is a first order or second order transition between them, it would be the same. It's much more interesting when it's a second order transition because then we can say more. And many examples that I'll give, one can actually prove that these are second order transitions. I'm going to make a few more preliminary comments which are more about terminology, and that's basically because when I saw people from the two communities talk to each other, there has been some confusion in the terminology. So let's get this confusing terminology out of the way so that we have only the conceptual confusions to be confused about. So all gauge groups will be compact in this talk. Compact in the mathematical sense, for me, U1 is a compact group. There's a non-compact group known as R. R is a non-compact group, U1 is compact. In condensed matter physics, people talk about compact U1 and non-compact U1, and maybe even later in this conference you will hear people talking about the CP1 model, the compact CP1 model, and the non-compact CP1 model. For me, CP1 is compact. It's a compact space. What is called non-compact or compact in condensed matter physics is whether we do or do not add some terms to the Lagrangian. This is a more dynamical question. It's what we integrate, what the integrand is. Compact or non-compact is what the range of integration is, what we're going to integrate over. And I'm going to follow the high energy definition because I really think it makes more sense and is less confusing. The second thing I'm going to emphasize is that all Chern-Simons terms have to be properly quantized. And I said that many times last week, and I was given some hard time by people in the audience. It doesn't really matter. Yes, it does matter. This whole business, this whole story about topological phases of matter is, I underscore the word topological. And the whole story is about integers. That's what makes the story so beautiful. You have a very complicated system, and in the end, you measure a third. And you don't say that you measure 2.59, you measure 1/3. So the whole story is about integers, and being careless about factors of 2 in the normalization of integers is like not doing anything. So this is a point I really emphasize. I think for the people who are more mathematical in the audience, say, why does he even bother to tell us that? It's completely obvious. for people who are more from condensed matter physics, you have seen that last week, that people on the honor say, yeah, but sometimes I manage to get the right answer by being careless about the normalization. Yep, sometimes you get the right answer by being careless, but this is not practice that should be followed. And the last thing about terminology is the fermion determinant. This will make little difference in this talk. The fermion kinetic term is that, and that's what is often written this way in my conventions. So that would mean in the standard terminology that it's U1 level minus a half. So the a half here refers to the fact that we have here 1 over 8 pi rather than 1 over 4 pi. And I will write it this way because I follow rule number 2, that all Chern-Simons terms have to be properly quantized. And I've said quite a lot about that last week, so I'm not going to repeat it. If you're really interested, I hope the talks are online.
So the objection is that second term is so well defined.
The second term by itself is not well defined. So I'm going to write it this way, and when I integrate over size, there is a phase which is eta, and this eta has some specific normalization, and it is gauge invariant. The fermion determinant is gauge invariant, but it's not time reversal invariant, which the statement I now said is the opposite of what is common both in the high energy and in the condensed matter. So this is not high energy versus condensed matter. This is not me, I learned that thing from Witten against everybody else, except the mathematicians. So, but this will appear slightly later differently. Now going to the history. I think that the history of this subject is really fascinating because these were 3 totally independent lines of research which converge on the same set of ideas. This is a very interesting lesson for funding agencies who try to put us in boxes. This is math, this is string theory, this is particle physics, this is condensed matter physics, and so forth. And there's cross-fertilization between the different ideas, between the different schools, and this is something that should be encouraged, not discouraged. The second thing is that I'm going to have a lot of conjectures here. And one of the reasons I find these conjectures appealing and interesting and believable is that the same set of conjectures follow almost independently from totally different starting points, as different as you can. But having said that, describing the history just following one of the 3 routes and not giving the others, does not do justice to what was actually happening, because some ideas appeared earlier in the other places. And second, misses some of the beauty of the subject. When the same set of ideas come from different places, even if none of them is really rigorous, and if none of them was really proven, it gives us more confidence that the same conjectures were motivated by 2 totally different things. And I've given a lot of talks about it, so I'm not going to review it in detail. The first route is the condensed matter, 3D quantum field theory route. The second is dualities and supersymmetric theories. And the third is large N, and they all converge. I'm not going to review it here, but I will mention some of the applications later. And since this is such a long story with a long history, I decided to put all the references on one slide. In fact, this is not all the references. This is a subset. And one person should really be highlighted. It's Ofer Aharoni, who played a crucial role in 2 of these 3 different routes. And
all the ideas, they converge to like all the ideas.
Sorry,
The common ideas are like all of the common ideas.
the common ideas, I'll show them exactly where they come from and how the different views came from different directions on the same set of conjectures. So here are the conjectures. So I'm going to assume here, postulate, a number of conjectures of dualities between scalars and fermions. And the dualities will be labeled by 3 integers. There would be NF scalar fields. In this case, they are complex with some 5/4 fixed point. So it's like the Wilson-Fisher fixed point coupled to some gauge fields. And there are n colors of scalars. So there are NF times n scalars in this formula. And we have a 5/4 fixed point, and we tune the phi squared to 0. And the gauge group could be SUN or UN. And this subscript here is the level. UN has 2 levels, depending on the trace of ADA or the trace AD trace of A. So there are 2 Chern-Simons terms we can write. There are 2 quadratic forms. So this is a Lagrangian of a scalar theory coupled to some gauge theory with some levels. And here we have NF fermions coupled again to UK or SUK or UK and UK, and again with their levels. The details are not important. The fact that the level here can be half integer when NF is odd was explained on the previous slide. Now, the details are not important for the sake of this talk, but if you want to work on this in this field, and you change one of these things, you change the sign here to plus, the duality is not true. So everything relies heavily on getting all the normalizations here straight. And there are cousins of that with SON and SPN gauge theories. Here the scalars are complex, but here the scalars are real. So this is a whole bunch of conjectures, which might or might not be true, but that's what they are. And
the boson have an N component. But the fermion, each family of fermion, do they have a K component?
That's correct.
Okay.
Yeah, so the number of fields is different on the two sides. So here, so let's discuss this one to be concrete. We have N times NF complex phis. And here we have K times NF complex fermions. So the duality might or might not be right, but the statement is very, very explicit. I want to make sure that this is very, very explicit, and now we have to test whether it's right or wrong. There was a question here? None. And if you examine it in more detail, you see that it's sometimes easy to kill a duality. It's very hard to prove it, right? So if NF is too large, you see that this duality, as stated here, cannot be right. So there's already a bound showing that we don't just write a conjecture and then say, okay, that's fine. We should subject it to as many tests as we can. So why do we believe any of this? So that has been supported and partly motivated by these three different routes that I mentioned, three really independent lines of investigation with different cultures using totally different methods. The first is ADS CFT and large N. Take any of these dualities, take N to infinity and K to infinity with finite ratio. If you do that, the theory becomes calculable. There is a second order point to answer your question. In this range of parameters, we can actually prove that there is a second order point and compute the critical exponents in perturbation theory. We can put the theory, say, on S3 and compute the S3 partition function, and this was done by some of the references I mentioned, and the answers match. So at least in one range of parameters, N over K going to infinity with finite N over K, so it's still one parameter that we can still dial, this N over K. As a function of this N over K, there's a non-trivial map between the two sides. If you remember, one of them has roughly N and K interchanged. It's quite, the formula is a little bit more complicated, but when N over K small or large are being exchanged, and this can be tested. So in this range, we can actually test it, and the transition is second order. There are similar supersymmetric dualities, which again cannot be proven, but have a lot of evidence that they are right. These dualities were first guessed in 3+1 dimensions, then they had descendants in 2+1 dimensions, and they were subjected first to some tests, then they were embedded in string duality. So if these dualities are wrong, string duality is wrong, and this is common in dualities. We have a lot of conjectures, but they are not independent, and if you remove one of them, you disprove one of them, the whole structure collapses. Furthermore, in supersymmetric theories, there is a technique known as localization that allows us to perform exact computations. And then exact computations were done in the two sides of the duality, and they match. And they match in a highly non-trivial way. In some cases, to prove that they are exact, you really have to use state-of-the-art mathematics about some special functions. Some of these special functions had just been discovered, some hypergeometric elliptic functions. This is way above my knowledge. But if you look at the formulas that have to match and the identities that have to be true, it's really amazing that it's true. No question about the fact that the supersymmetric dualities are true. QED. What about QED? I'm talking about the non-abelian theory, but that was a joke. And you can start from the supersymmetric theories, and turn on operators that explicitly break supersymmetry and flow to the infrared. That's not rigorous because the flow might not be smooth. But if you nevertheless do that, you land on these dualities. So that gives you more evidence that this is right. Also, the structure of the formulas is right. And there were also ideas originating from particle-vortex duality in the condensed matter literature. This was the first was Peskin, and then Halperin and Dasgupta, and then many other followers, including recent boson-fermion dualities that also seem to match. So that's the third, and these are really three different distinct lines of investigation using different methods, different cultures, different people, and they all converge on the same formulas.
Could you rewrite your table of quantum groups in the last case?
It's not quantum groups. These are ordinary gauge theory groups.
Would you relate it to thinking that it does
I don't know how to put it in quantum groups, but I can connect it to something that is morally equivalent to that. I'm soon going to connect to that. Also, we can assume some of these dualities and derive others, so the assumptions are not independent, and I'll do some of that later in the talk. And we can turn on mass deformations in these theories. We have mass terms on both sides. We can do that and flow to the infrared and find something, and land again on the same list. It doesn't prove that it's right, but it shows that if one of them is right, the other is also right, and we had examples of that last week. And that's the point I mentioned earlier. We can flow to the theory with no flavors, or just substitute NF equals 0. So there are no scalars and no fermions, and that's the answer also to your question, and also to your question from the other day. In this case, we have a duality between two different Chern-Simons theories, no matter fields. That duality turns out to be a level rank duality. So A, at this point we can prove it. Level rank duality can just be proven. So at that particular case, we have another test of this whole structure. Namely, we got to a place where we can compute, and then we landed on our feet. It could have been wrong, but this didn't happen. And not only that, we have that. Also, level rank duality is another notion of duality, where we don't have an exact change of variables from one Chern-Simons field. So we have two different Chern-Simons field theories, and we do not have an exact, explicit change of variables from one to the other. But here we can prove that the duality is right by computing everything. All the observables are computable, and the duality is right. So these dualities are generalizations of this level rank duality. And since level rank duality is known to be deep, and it appears in various different contexts, it's nice that it also appears here as a very special case, the case with no matter. So it doesn't prove that it's right, but it shows that in one corner, when we don't have the matter fields, we land on our feet and we land on something deep. So that's encouraging. And you also asked me the other day whether it's connected to level rank duality, and it is. And finally, we should discuss the global symmetries and the 't anomaly matching. And depending how much time I have, I'll try to do that later in the talk. The quick answer is that it works. Yes?
So what all those duality come from level rank duality?
No.
This will be the unifying feature.
No, that's a consequence of that. The logic is backwards. Level rank duality of Chern-Simons theory is a special case when there are no matter fields.
Yeah.
This is a statement about topological field theories. As Wang emphasized yesterday, topological field theories, interesting, rich, and complicated as they are kind of the simplest, most trivial quantum field theories. These theories are not. These theories have interacting, fluctuating degrees of freedom locally. They have correlation functions that are highly non-trivial functions. They are not topological.
What I mean is that when you have level rank duality, when you add matter field, that can generate all the known duality.
But it's a question how to add them. You could have said, here is a wrong thing. Let's take level rank duality and add scalars to the two sides. That's not true. That's an example of why it's not true. So even at the heuristic level, you generate wrong statements. You say, there's a cousin of that. People ask me about flux attachment. Say, this is just flux attachment. That's not true. If you take the formulas from flux attachment, which I emphasized then were non-relativistic for massive particles, and here I talk about massless particles, and you could say, well, it doesn't matter. Let's do that anyway. If you take the formulas from flux attachment, you land on dualities of massless particles that are not true, that you can check and they are not true. These statements are more limited. I'm saying you have to add a boson here and a fermion here and shift the Chern-Simons level by this or that. So it's more than just saying it's level rank duality. The converse is true. If you assume this is true, you derive level rank duality. Level rank duality does not need a derivation because we know it's true anyway, but I think it's clear what I mean. So instead of going through all the most general cases, let us substitute some special values and see how it works, and I'll give examples of various kinds. First, I'm just blindly going to substitute nf equals k equals 1 in this duality. So this is one of the dualities. So here I have SU1. So SU1 is easy. It's not there. And then what I have is a complex scalar with 5 to the 4th interaction couples to UN level 1. So this is an interacting scalar theory, and it flows in the infrared to a free complex fermion. So we had example of that conjecturally. But this is a very strong statement, because here you have scalar fields with some 5/4 coupled to gauge field with UN with level 1. So the case n equals 1, I motivated it last week in a lot of detail. But here we have, it's a whole family parameterized by n. All these interacting theories flow to the same complex fermion. And in the case n equals 1, which we discussed last week, this is the O2 Wilson-Fisher point coupled to a U1 gauge field, and it again gives us conjecturally a free complex fermion at long distances. So again, this might or might not be right, but it's a very explicit statement, which is worth checking. And if you just look at that, you see, saying that this thing follows from level rank duality, as you said, I wouldn't even know how to start, because you have to use level rank duality of SU1. So the statement here without that is that SU1, which is empty, is the same as UN level 1, which is also kind of boring. Yes, so that's is much more than just saying level rank duality. And
oh, I see. It's because SU1, so there's no gauge field in front.
Yep. And more details of that, we discussed it, a lot of it last week, but it works for any n. Duality is more interesting when one side is free, because then we read this is the question and this is the answer. The free fermion can be identified in the UV as a monopole operator in this theory. So we can actually identify the operator here. The mass deformation is turning on psi bar psi here, and that translates to turning on, so psi bar psi here, that translates to turning on a phi square term here. So in the context of your question, this is analogous to the SU2 theory, and this is analogous to the U1 theory in 4 dimensions with n equals 2 supersymmetry. And time reversal is not a symmetry here, but there's a new time reversal that acts non-locally on this phi that appears in the infrared, and it has an anomaly, and we discussed that in detail. So this is the complex version. There is a similar story in the real case that was discovered independently by 2 groups, one condensed matter and one high energy physicist. Just take this duality that we mentioned earlier for SON, and just substitute NF equals K equals 1 equals 1. So again, SO1 will be trivial. And now we have n real scalars with some 5/4. So I use lowercase phi because it's real as opposed to uppercase, which was complex. So this is SON level 1 with scalars, and that's a free real fermion psi. So it's again a conjecture, but there's a lot of evidence that this is right. And here are some comments. Here, the magnetic symmetry, which before was U1, now it's Z2. So SON has Z2 magnetic monopoles. And these Z2 magnetic monopoles of the microscopic theory become the free fermions at long distances. So there is such an operator in the UV. The non-trivial fact is that by the time we are at long distances, it becomes a free fermion with a canonical dimension of a free fermion, which is 1 in these dimensions. Charge conjugation, which is a symmetry here, is mapped to monopole number modulo 2. The mass deformations can be explored, the fermion here and the boson here. Time reversal, it's the same as before. I'm going to give another example of this web of duality that I mentioned, which I think is quite illuminating. and highlight some of the points I made before. So I'm going to study 4 different theories. In fact, there are 2 others that I could add, but they don't fit on the slide. So the 4 theories I'm going to study are fermions with U1 level minus 3/2, the Wilson-Fisher theory with U1 level 2, fermions with SU2 level minus 1/2, and the Wilson-Fisher, these are scalars, with SU2 level 1. So these are 4 different theories. What do they have in common? The first 2 has a global O2 symmetry. There's a magnetic symmetry in both cases, because there's a U1, and there's some charge conjugation that enhances it to O2. So these 2 theories, in purple, have a O2 symmetry. These 2 theories have an SU2 symmetry that rotates, because if the gauge group is SU2, SU2 is a pseudo-real representation, and therefore there is an SU2 global symmetry. In fact, the global symmetry is SO3. So these 2 theories have the same global symmetry, but they are different. These 2 theories have the same global symmetry, but they are different. And this pair and that pair, they don't even have the same global symmetry. So they're clearly different. Yet, we can flow to the infrared and use our long list of dualities. So let's first compare this and that. Here it's U1 and this is U1. That's on our list that we had before. So these 2 theories should be dual by the UU duality. But U1 is the same as SO2. So this pair also appears in the SON list. The fact that the same pair appears in both with the same shifts, plus K, minus K, plus a half, minus a half, is a test. This pair, it's U1 and this is SU2, appeared in the SU2 with U duality list. So that appeared on a different list. So it's there. SU2 is the same as SP1, so the duality between these 2 appears in the list of SPN theories. And finally, so we say this must be dual to that. It appears twice on our list in 2 different lists. This is dual to this, and this is dual to that. So this should better be dual to that, and sure enough, this is some other entry in our list. So that by itself is a consistency check, that we could move between these theories using different rules, and we come back to where we started. So all these theories flow to the same infrared fixed point. And since here the global symmetry is SO3, it means that this O2 symmetry must be enhanced in the infrared to SO3. And in fact, just by looking at the fact that the SO here and the U here, UU duality here, and checking how the global symmetries match, is O2, if all we have is the O2, they do not match correctly. They match correctly only within SO3. So that by itself tells us that there must be a larger SO3 symmetry. So first of all, it's a non-trivial consistency check. And there's an enhanced SO3 symmetry. Now, we have seen things like that in 1+1 dimensions, and in supersymmetric 2+1 dimension theories, where we start in short distances with the U1 symmetry, under which some monopoles or some topological excitations are charged. And at long distances, the abelian symmetry, or the O2 symmetry, becomes SO3. The symmetry is enhanced in the infrared, and it is enhanced using monopoles. I'll be more explicit about that soon. What was the question? Yes.
So the statement is that the duality is true whether or not you have the O2 symmetry, but basically you're saying that if you have, like, you can't just have the O2 symmetry.
That's correct. If I try to explore this duality with the UU symmetry duality, the map between the symmetries here and here is one thing. The U1 is mapped correctly. The discrete symmetries are mapped differently. And in the SO, there's another map of the discrete symmetries. So you say, how can that both be consistent? They'll both be consistent if both of them exist at long distances. And that actually was the first thing that tipped us that there must be an SO3 symmetry, and then realized we can also get it from here. So the fact that all I'm saying is that all these dualities exist on the various lists, and in the various lists there's a lot of details how the discrete symmetries are mapped, and in this case the map between them is non-trivial. Question?
Yeah. In order for have an exact emergent symmetry, you need a correlation length much longer than cutoff scale.
That's correct.
So that here means that there's a kind of critical point, and at critical point in all these whole theory.
That's correct. That's correct. So in high energy physics, this is called an accidental symmetry. In condensed matter physics, this is called an emergent symmetry. And there is a sense in which this thing should also be called a quantum symmetry, in the sense that will be on the next slide. Enhanced, it's bigger. It was SO2. It's a subgroup of this SO3. So at short distances, we saw only O2. So in this description, we saw at short distances an SO3, which became the same SO3. Nothing was enhanced. In this description, sorry, you look here, in this expression, in this side, we saw at short distances O2, but at long distances, the O2 became a bigger group, which is SO3. That's a non-trivial statement. It might or might not be true. This is a conjecture. Everything here is a conjecture. But I'm moving in the space of conjectures, trying to see whether I can have a coherent picture, and I'm always staying on my feet. And here I managed to stay on my feet in this interesting way.
So if you just took the two theories on the left and you started studying this critical point and you found that it only had O2 symmetry.
That would prove that most of this talk is wrong. It's a strong statement, and it can easily be proven. Well, doing it on the lattice is not so easy because of the Chern-Simons level. But I actually talked with some condensed matter people who told me that there are tricks to simulate these particular things, and then this could be proven or disproven. So if it's proven, great. I will not be shocked. If it's disproven, proven on the lattice, because it will be numerical. If it is disproven, then I will have to go back and see whether anything can be salvaged here. I would like, and the new current that enhances so there's a new current here, which is a monopole operator, which enhances the O2 to SO3. I want to say some more about that. So let's review again some special cases. And we have a long list of cases, right? These were 6 infinite sets. Every one of them is labeled by 3 integers. So there's lots of room to be wrong. But I want to I highlighted some special cases. So let me highlight some other cases. Let's start with U1 level 0 with phi. This is the gauge Wilson-Fisher theory. And if you look at the list, it becomes phi hat, which is just the Wilson-Fisher theory or XY model, and this is known as particle vortex duality. We discussed it last week, and we'll soon see how it fits with our dualities. And this theory is dual to U1 level 1/2 with the fermion. That's QED in the sense of quantum electrodynamics. So we discussed that last week. This is 2 + 1 dimensional QED. It's dual to the gauged Wilson-Fisher theory or to just the Wilson-Fisher theory. And then I'm going to increase the label here. So here the label is 0. So when the label here is 1, this was a free fermion. That was earlier in the talk, and it was also last week. When the label here is 2, this is the system that has an enhanced quantum SO3 global symmetry. So notice that the label here keeps growing. And in all these examples, we need phi-4, and we need to tune to the tune phi squared to 0, and we have to hope that there is a non-trivial fixed point. But I would like to see some similarities along as we go down the list here. So in all of them, we have U1 level k, and the U1 level k has a monopole operator of spin k over 2. We discussed that in the first lecture last week. The monopole operator of U1 level k has spin k over 2. And let's identify it on the other side. In particle vortex duality, the monopole operator from here has spin 0, and that's the order parameter of the XY model. So that's a scalar field. Here, the monopole operator has spin 1/2, and it's the free fermion on the other side. We said it last week, and we said it again today. Here, the monopole operator has spin 1, and therefore it's sitting there ready to become a conserved current. So as we flow to the infrared, its dimension starts going down, and if the duality is right, or the statement of the duality is that this operator started at very high dimension, by the time we're at very long distances, it has dimension 2, and it becomes a conserved current. Have we seen that before? Yes, in 2 dimensions, 1 + 1 dimensions, when we talk about the compact boson, a particle on a scalar, at large radius there is a U1 symmetry, actually U1 times U1. And as we make the radius closer and closer until eventually it hits the self-dual radius, the U1 symmetry becomes SU2, and it becomes SU2 by the new current being what was previously a winding mode. So a winding operator for large radius becomes the other conserved current that enhances U1 to SU2. This is the context where this is known as a quantum symmetry. The other place where this was seen, just one second, the other place this was seen, I told you that all these theories have supersymmetric cousins, or maybe I should say supersymmetric precursors or supersymmetric ancestors. And in the case of these supersymmetric theories, in 3 dimensions, 2 plus 1 dimensions, there is a phenomenon known as 2 plus 1 dimensional mirror symmetry, not to be confused with the mirror symmetry of Calabi-Yau manifolds, although they are quite related. So there is a phenomenon known as 2 plus 1 dimensional mirror symmetry. And the phenomenon of this 2 plus 1 dimensional mirror symmetry is that you start from a theory that has an abelian group, symmetry group. There might be some discrete parts, but the continuous parts are abelian, which turn out to be the Cartan subalgebra of a non-abelian symmetry, which appears in the infrared. So it's very much like the phenomenon we see here. The phenomenon of enhanced symmetry in this case is essentially the same as the phenomenon that was seen earlier in 2 plus 1 dimensional mirror symmetry. So there was a question here. No, it was behind you. Somebody here in the back, and I said just one. Okay.
I try to clarify this half U1. So you have a psi is a QED, so it's a directional band coupled to U1 gauge field. Then on top of that, you add additional.
I do not. So in my notation, in my notation, I do not add anything. This is a fermion coupled to a gauge field. This is the thing
so
that
this
some.
mean it's a U1 half level.
That's correct. Some people say that this theory is not gauge invariant, and therefore you have to add another term which is also not gauge invariant to cancel this gauge invariant, lack of gauge invariance. This statement I just made is imprecise. The proper way to say that is not to add anything, but I will still use the notation with a half because it's convenient. So what I really mean by that is a fermion coupled to gauge fields and nothing else. And yes, last week I've gone through a lot of detail into that. And if you're interested, it's online. Yes?
Sorry, but you are so far comparing degrees of freedom. But what would you really compare in this duality? The partition function?
Okay, I would like to compare everything. I don't know how to do that. Yeah, I would. The claim is that all of them are the same. I don't know how to prove it. That's a claim. Now, what can I prove? I gave a list of tests.
The fact that they are the same degrees of freedom doesn't mean that they have the same theory.
That's right. So, in fact, that's right. In fact, they don't have the same degrees of freedom. The beauty of the story is that they don't have the same degrees of freedom. The theories here have only fermions, only bosons. This theory has fermions and gauge fields. They don't have the same degrees of freedom. So the first thing is to match the operators, not the degrees of freedom. The operators. So the first thing we would like to match the symmetries and the operators charged under the symmetries. Then we would like to match more. So we would like to compare, say, correlation functions. I don't know how to do that. I don't even know how to do that in the supersymmetric case where there is no doubt that the dualities are true. I can make deformations. I can take the theory on the left or the theory on the right and give mass to phi, for example, and decouple it, and then it's a lot of work. We have to go to the infrared, and it depends on the sign of the mass, etc., and we can do that on both sides and check that both of them give the same answer. It's highly non-trivial that it works, because every step looks like it's not going to work, and in the last step, things cancel and it works. It would be much nicer to have a proof. At this stage, I would even settle for a numerical proof. But that's a statement. Yeah, that's this slide. That's right. That's right. But it's still not rigorous for continuum field theory, for reasons that I'll be happy to discuss. But whatever can be done will be welcome, because the evidence some statements here have more evidence, some statements here have less evidence. Some of them I trust more than others. I'd like to get the whole picture straight.
Sorry, this is very naive. But if you don't have explicit functions that take you from one system of degrees of freedom to another degrees of freedom, what exactly are you comparing?
Well, it's not naive at all. It's a very deep question. There are really several different questions here. One, in dualities, can we really make a change of variables from one to the other? This is the case in Kramer-Vanier duality in 2 dimensions, or in F square in 4 dimensions. That's not the case in the typical duality that has been dominated high energy physics for the last 25 years or so. In none of these dualities do we have a change of variables. And this goes to all the field theory duality literature, the string duality literature, and so forth. There's no change of variables in any of them. And that's why it would be really... So what am I comparing? So there's evidence for the conjecture. These are all conjectures. And there are evidence. There's evidence. And sometimes the evidence is more detailed and sometimes it's less detailed. So in the different cases, we compare different things. In the supersymmetric dualities, we can compare various partition functions using localizations. In other cases, like n equals 4 super Young-Mills, at large n, this is an integrable system. So some anomalous dimensions are computed explicitly as a function of the coupling constant. In other cases, it just fits nicely with this whole collection of conjectures, which can be proven differently. In other cases, people can actually sum up instantons and derive one case from the other. In the n equals 2 in 4 dimensions, and Nekrasov summed up the instantons and derived the answer. If you wish, even before he did the computation, physicists had a lot of evidence that this was right. Mathematicians didn't have a proof, but I think it became quite clear that this must be right, just by the results that came out of it. That's not a proof, and it would be nice to have a proof. So that's in the supersymmetric case. Without supersymmetry, there's much less evidence, and I tried to enumerate it. At large n, connection to the supersymmetric theories, and so forth.
Yeah, you mentioned about the numerical test, so let's use the first line.
Yeah.
So this is QED with the fermions.
Yes.
So in order to do numerical tests, seems we need to put that on the lattice, or you have some other way.
That's right. That's right. So the same theory with 2 flavors. There's huge literature. So first of all, I would say this is controversial. People try to put that on a lattice, and what QED does is still controversial. As of last week, there was a paper doing this theory with 2 fermions, which also fits nicely in this picture. And there, it's easier to put on the lattice. And these people simulated it and found numbers that are consistent with the duality. That's with 2 flavors. With 1 flavor, it's harder, because the UV theory is not time reversal invariant. But, okay, it does not... So all of you saying that it's harder to test. It doesn't say that this thing is wrong. But if you accept that the duality with 2 flavors is right, based on the evidence, I think it will not be too difficult to derive the duality with 1 flavor. Usually, if you have a duality with more flavors, you can flow down to dualities with fewer flavors. So I can see that there would be a combination of some of these dualities being proven numerically. So it's not proven. Give a lot of evidence that we're convinced it's right numerically, and then others follow logically for them. That's why moving in this space of conjectures and seeing conjecture 1 implies conjecture 2, which implies conjecture 17, etc., is useful, because if you disprove one of them, you see what will go wrong, and if you prove one of them, you also see what will go wrong. Yes?
As far as I understand, the statement is not that both theories on both sides are the same, but the infrared behavior is the same.
That's correct.
Which means that there should be some dictionary between long-range behavior correlators on one side.
That's correct. That's correct. Yeah, the dictionary is between the operators. And that's why I worked so hard to say that the monopole operator of one is the fermion of the other. So correlation functions of monopole operator on one side are the correlation functions of, say, the fermions on the other side. How am I doing with time?
You have no time.
No time. Okay, so I... I can tell you what I skip. So I prepared to talk about the global symmetries and how the global symmetries are subtle. I prepared to talk about how we couple them to background fields and how when we couple them to background fields, we learn more about these dualities. We can derive some duality using another. There's a whole technology that goes into it. Also, when we couple them to background fields, this is where the toothed anomalies raise their head when we couple them to background fields. And then we have to check that not only are the global symmetries the same, the toothed anomalies are the same on both sides. But I hope that Zohar will do that in his talk, at least for some of these examples. So you did not miss much by the fact that I skipped that. The upshot is that the global symmetries match in a highly non-trivial way. The global symmetry groups are really non-trivial in the sense that there is some kind of naive global symmetry, but the symmetry that acts faithfully is only a quotient of the global symmetry. And that has to match between the two sides. And furthermore, because of this quotient, when we couple them to background fields, there are more bundles that we can subject the theory to. We can put the theories in more bundles because of this quotient in the global symmetry. And if we have more bundles, we have more observables, and there are more tests. And these tests, again, work, and they work, and I really feel that it's quite miraculous. The other thing I wanted to do with that, sorry? Metric, I include the metric also. There are metrics and there are anomalies associated with whether the model is spin structure, whether I do or do not need the gravitational anomalies, the framing anomalies, and whether the model can or cannot be placed on a spin manifold. That's also kind of a discrete gravitational anomaly. All these things match. And you know, in this game, since these are all conjectures, one of them fails, a lot would fail. So, and after a while, you know, after a lot of tests, you begin convinced that it's probably right. I also wanted to show how, assuming this duality, particle-vortex duality, the bosonic standard boson-boson particle-vortex duality follows logically from it, and derive fermion-fermion duality, and doing it more correctly, paying attention to the proper quantization of the Chern-Simons terms. And I've done some of that in my talks last week. So because of lack of time, I'd like to summarize. Duality is ubiquitous in physics. That seems to be kind of a guiding principle. We use different variables to discuss the same physics. These are two different theories that are really fundamentally different, and they flow to the same behavior at long distances, or they are exactly the same on the nose, but we use different degrees of freedom to describe them. And I really like the fact that ideas from different branches of physics converge on the same set of dualities. I don't think this story could have been told if you removed, since I lived through the period that these things happened, I don't think this picture could have been suggested without having all three lines of investigation. And I can really show where the clues from the different lines were essential in the other lines. So when people talk about, I'm only interested in particle-vortex duality because I'm a condensed matter physicist and that's what we do, and ignoring the fact that this is one of a three-parameter family of dualities, a three-parameter family that can be tested at large n, that you really miss fundamental part of the story. Similarly, the fact that this thing comes from supersymmetric dualities, if you don't know that this comes from supersymmetric dualities and the tests it was subjected to there, you might not have enough confidence in this picture and you will not see how this works about. And again, referring to Wong's talk, yesterday he studied kind of the most general modular tensor category. And it's true that in experiment in condensed matter physics, you're not going to find all these sophisticated modular tensor categories. You're going to get some of the simpler ones if you are lucky. Yet, it is essential to put it in the right context and to understand it as a representative of a much bigger story, which is labeled by more integers, etc., and study them even if experimentally, you know, only the bottom example is realized. So it's much better to see it in the bigger context. And that's the point I emphasize here. You should really put it in the bigger context, because otherwise you really miss a lot of the underlying structure. And more specifically, we showed a really rich web of dualities, assuming some of them leads to others, and there were many cross-checks. There were boson-boson dualities. The hallmark is the particle-vortex duality, boson-fermion dualities. I showed a long list of them, and fermion-fermion duality that I skipped at the end of the talk. And I believe that there are many other dualities to be found. I think this is just the tip of the iceberg. I think this is a rich story that, and we can just use the techniques that I mentioned here and the techniques that I skipped by gauging global symmetries to derive others. And the others might or might not be interesting dualities, but there's a machine that produces them, and it's worth doing it. I'd like to hope that there are new dualities that don't follow from this machine, using totally new ideas that are not just turning the crank and doing the same thing again. And what I really hope is that somebody will either prove these things or put them in the right framework, because at the moment we just stumble on these dualities. It's clear that there's some underlying principle that organizes it all, and I don't know what it is. And so I think I'll stop here. Thank you.
So we're running late. That was just the most urgent questions.
Just one quick question.
Where's someone?
Oh, sorry.
So I have a question about the nature of the fermion operators. For example, in the duality conjecture by Son, on the one side there are some p-relativistic fermions, and on the other side there is a theory with a Chern-Simons field. And then you mentioned that the fermions of one theory become monopoles of the other, and both theories are relativistic, so naturally there are two spin components. But then Son also conjectured that the relativistic theory with Chern-Simons field actually describes strongly interacting non-relativistic electrons in the first Landau level, which only have one spin component. So how should one construct this single electron operator?
There are really two questions. One is about the duality that Son conjectured, and second, whether it has anything to do with fermions with a first Landau level at half filling. The second question I'm not going to address. I know very little about it. The first one, I would like to say a few things. First of all, the duality as he wrote it is imprecise because it has Chern-Simons terms which are improperly quantized. So that's the first thing. So we should fix that. After we fix it, some people said that what all this is, and it's not just him, it was him, and then there were a few follow-up papers by other people. Why don't I put the formulas here? But after we have done that, there was a claim that you can see often in the literature that this is a free fermion on one side, and okay, these are the other authors, and this is the free fermion on one side, and these are fermion coupled to some gauge fields. So this more complicated expression actually does make sense. Everything is properly quantized. And people said, this is the free fermion, and this is QED in 3 dimensions. This statement is fundamentally wrong. The factors of 2, you could say they don't matter in some cases, in other cases they do. The statement I just made is fundamentally wrong. This is a free fermion, that's correct. This is not QED in 2+1 dimensions. And it differs from it, not just in how I normalize some field, but if I integrate out things incorrectly, as I did last week, this theory should better be called U1 level 0, not U1 level 1/2. So this is a theory that has different critical exponents. QED in 2+1 dimensions, as I said, is dual to the XY model. It's an interacting fixed point which has non-trivial critical exponents. This is really a very complicated quantum field theory, very interesting and complicated quantum field theory. The statement of the duality is this theory is really free at long distances. So it's fundamentally different. It's not just that, you only take monopole charge 1 but not monopole charge 2 or the other way around. It's much more interesting. This theory at long distances is a free theory. QED in 2+1 dimensions is an interacting theory. And that's also connected to your question. The theory that is I called QED with U1 level 1/2 is an interacting theory at long distances. That's the claim. This theory at long distances, even before you do anything else, you cannot have both statements right. You cannot say that QED in 2 plus 1 dimensions with one fermion is both dual to the XY model and being a free fermion. This cannot be right because one of them is interacting, the other is not. So I'm putting some order here. The theory that is dual to the XY model is what I call U1 level 1/2. This is a fermion with no editor and Simons-Term in my notation. This theory, if at all, should be thought of as U1 level 0. So it's a different theory. So I hope this is a... There is a fermion operator here, and it is made out of monopole operators on this side of the duality. There are two. Well, in the relativistic theory, there are always two fermions because it's a doublet of SO2-1, of spin 2-1 to be precise. I cannot tell. If it's non-relativistic, I don't know. So there was a question here. Wang?
Just quickly, do you think there's a similar real web of duality with class 1?
Okay, in the supersymmetric case, yes, there is. In fact, this is how this whole story started. This whole story started from a very similar web of dualities in 3 plus 1 dimensions in supersymmetric theories. So in supersymmetric theories in 3 plus 1 dimensions, I know there is. In fact, I kick myself for not thinking about this in the 90s because I knew everything about the dualities in supersymmetry in 3 plus 1, and I knew everything about the dualities in 2 plus 1. I looked for non-supersymmetric dualities in 3 plus 1. I couldn't find anything, and then I abandoned it instead of going to 2 plus 1. Because otherwise, this would have been done 20 years ago. But having said that, I do want to say that I strongly believe that the answer is yes. I think there are such dualities in 3 plus 1. They will be a lot more subtle and much, much more interesting.
That's what it is.